talk about some of the work that we're doing at Idaho National Labs. My next slide is going to show you is a snapshot of INL's work in this particular area. The department is a part of the the Clean Energy and Transportation Division, the Energy and Environmental Science and Technology Directorate at the Idaho National Labs. Idaho National Lab is one of the 17 national labs belong to DOE, but we are very unique in the essence that we are belonging to the Nuclear Energy Office. So we are not a basic science lab. We also not an NSA lab or other offices. So it's in unique sense that INL focus on energy production through nuclear reactors, as well as the distribution, and that's why the energy storage and environmental impact, as well as the grid integration, is part of our mission to deliver reliable grid infrastructure for transportation as well as for other energy applications. So with that in mind, the scope of the work we have is quite broad, which means we look at the energy storage not only as a device, but also as a system in the larger scale of grid operation. So if you look at the first slide I'm showing you here is in my lab, actually, we are evaluating battery technology from materials level all the way to the whole grid infrastructure application. And we are in the very broad scope, we also try to apply the principle-based understanding in performance and to understand how the performance can be correlated with component level as well as system issues, and how to address a broader context about durability, reliability, and safety aspect in the energy storage, as well as the charging infrastructure for the transportation electrification, and also for the grid stability in regarding the stationary energy storage application as well. So with that in mind, I think the current focus of our approach primarily is, again, it's not just evaluation, demonstration, and collecting data, but also more deep into the data analytics to understand how to detect the gap in the technology, as well as from materials aspect order to the cell design, to the battery operation, to the integration of the system control, all the way to the grid distribution. On the vehicle side, we also have a lot of charging infrastructure issues on the vehicle platform as well as on the charging station utilization. So it's a very broad aspect. Currently, we focus on two major aspects. One is how to develop high energy batteries. And in that scope, we are working with DOE, particularly under the Battery500 project, try to understand how to design a very high energy density, high specific energy chemistry into a real cell design. On the charging infrastructure, we focus on the fast charging technology, so not just on the battery side, thermal management, as well as the characterization of the performance and the impact on the battery life. We're also looking at the charging infrastructure regarding what kind of charging technology, connected, wireless. We do a lot of evaluation on different technologies to understand their interoperability. So, you can take one technology charging another vehicle platform and to see what kind of efficiency, the power quality, as well as many other issues in the operation of the charging infrastructure and the impact on the grid aspect as well. So that's a very broad implication about what we do here. The next slide I want to show you is in the context of durability, reliability, and safety. We have a very systematic perspective about how to assess risk and how to manage that. So we're not only looking at the system level or the component level on the device, look at their durability, cycle life, calendar life, performance, how to operate, how to install the system, but we look at the reliability also in the context of the environment they were operated in, both on the mechanical, chemical, thermal, and electrical aspect, how they impact the whole battery performance. And on that scope, we really looking at it how collecting the data to help the government develop policies and regulations, how to develop the correct procedures and protocol to collect information, and how to help them or the industry to facilitate the control and management of the system. So that's what we do here in terms of reliability. On the safety side, we actually also look into the human factors, including the driving cycle, duty cycles, all kinds of charging algorithm, how frequently the technology or the infrastructure use happens, and how the personal preferences going to impact the whole demand side management as well as distribution and other aspects. So those are the safety aspects that we address. So I think this kind of very consistent, systematic view about how to connect the battery from cycle life, end of life to reliability in the operation to the safety aspect, including the human factor impact, help us define what is the abuse tolerance that we need to address, not just through testing, but also to quantify that effect. So we know what's the impact on any catastrophic events, no matter it's smoke, it's fire, or the explosion. We know where they come from, how they address that impact to the safety aspect. So with that, I think currently our major technology challenges are to understand all the energy balance in the battery system, for example. The battery is a very unique chemical system, but you not only have chemical species you need to deal with, you also have electrical, mechanical, and thermal aspect that you need to balance through the whole device. And some are open, some are closed in the system. And so such a balance is a very delicate situation that we need to understand from a principle, not just testing and evaluation, collecting data. But from principles, we can begin to decouple those complicated systems into more systematically. We understand how to quantify different aspects of the impact from chemical gradient, from electrical field, from mechanical strength field to thermal generation and transport and dissipation issues. We also understand the interface is very important, and that help us to understand the perspective on a very large range of temporal and spatial scaling issues. So we have to do a lot of modeling from atomistic approach all the way to the whole system control, including thermal management issues. So we don't cover all the words, but we're working with a lot of entities, try to understand how to apply the principle to get us understand that aspect and impact on the battery performance. I think to quantify that kind of balance in a very realistic model situation, it's a very interesting, challenging for us at this point. So in the facility, we have quite sizable operations. For battery test center, we occupy more than 20,000 square feet of floor space that has all kinds of test capability from coin cells all the way to 500 kilowatts. We have channels to handle different usage profile, different power profile and needs for pulsing, for wireless, for connected charging and battery evaluations. We also have very complicated environmental chambers, including that can load up a significant size of pack to do both electrical, chemical, and thermal controls of the system. We also have a non-destructive battery evaluation lab that we can use to push the boundary, both on the mechanical, thermal, and electrochemical controls to see how they impact the battery performance. And we also have an electric vehicle infrastructure lab that we can pull the vehicle do extreme fast charging, for example. We also help SAE do a lot of wireless charging protocol development, as well as measure data, provide to the committee for code and standards. And so that's a very good example about what we do. As I said, we use principle-based science to understand the engineering approach. We're using failure mode and effect analysis quite significantly in the concept of quantifying failure modes and their effect on the battery performance. So that aspect is very different from most of the people that are more focused on looking at the conformity of the performance. We were more interested in looking at the outliers and anomalies and try to find out where they come from, using the variability to get a much more richer information about the battery performance issues and using them to guide all the evaluation of battery performance as well as the battery design. So it's different from the conventional wisdom. We actually use anomaly-based focus approach, look at insightful understanding of the cell variability. We address outliers and anomalies and looking mechanistic explanations about those properties. And we want to realize the true prognostic capability and the potential to accurately and precisely address those safety and reliability issues. So the high fidelity of the model is very important. I think we try to manage the prices of any kind of events so we can understand where they come from and how that can be addressed. So one example here is in the Battery500. In order to develop very high energy density batteries, we have to use lithium metal. So we are looking at the lithium metal electrode issues. We can show people how to use model to understand all this different field impact on the electrode surface and how it's going to change the lithium deposition morphology and the rate and also other aspects. How to apply pressure to suppress the dendritic growth. We also look at the variability. On the graph on the left-hand lower corner, you see we can do a 16 coin cells very consistently to look at their variability in the cycle life and understand all the mechanisms that cause those variabilities. And we can quantify those effects. So I think that's a good example to show you what I mean about this principle-based approach. We're also looking at from battery cell to the battery pack, from the laboratory testing to the vehicle operation in the open field, to understand how we can begin to correlate the stress from a known effect versus a very uncontrolled environment, and how to quantify those operational boundaries for any kind of high energy or high power applications. So those are the approaches that, for example, we just recently published a paper in Journal of Power Sources to compare the cell testing versus the vehicle testing and try to understand how we can see the variability from cell to packs and where all these differences can be analyzed in the way that we can quantify those differences. Finally, I think I'm getting to my last slides here. The grand challenging is really looking at a whole infrastructure integration. For nuclear energy lab, we're looking at the energy production from nuclear reactor, but we're also looking at a lot of renewable energy penetrations in the microgrids. We look at the transportation deep penetration. So in the future society, when you have different kind of mobility issues, how the connectivity of the vehicle to the grid, how the infrastructure support to support that kind of mobility application is very interesting. And I think we also have very strong cybersecurity research in the lab to understand how can interface and provide the security on the control issue as well. And so those are the work we are engaging right now. From 50 kilowatt fast charging, now we are at about 350 kilowatt charging infrastructure studies. We don't really have a charger at that level, but I think we are working with several suppliers for that. And eventually, we are looking at the upgrading the laboratory capability to about 2 megawatts and above to see whether we can begin to test a lot of storage battery configuration with the microgrids. And so those are the work we are undertaking right now. And so in the short summaries, I think we try to show people there was a very interesting way to integrate a systematic approach from the system analysis going back to the component to address all the safety, reliability, and durability issues, not just on the battery itself or on the vehicle, but looking at the interoperability of them and to see how the environmental and the use pattern, how that affect the battery performance. We're using principle-based approach, not just engineering, design or experiment correlations. We really go back to the principle to see how I'm going to predict that. We also look at a very systematic approach. From the system level, going back to the components. We don't start from materials to the system, but we go backwards from the system going back to the materials. And those had to be very capable to develop very high fidelity, understanding from experiment as well as modeling to validate everything we see. So I think that will be my conclusion for my talk. Thank you.
Thank you, Dr. Liaw. We'll allow a minute for some questions to be submitted before moving on to the next speaker.